I saw some old friends as I came to the city gate. They asked me where I'd been of late. I hadn't been anywhere, but what was I going to say? Two hopeful people.
Greetings, college algebra class. We are going to be going over lesson 1 today, and in lesson 1 we're going to be talking about sets of numbers. And as we explore this concept that there are different types of numbers, we will be going through each of them. We will start with the natural and move on to all the real numbers on the number line, and then even some that exist outside the number line. So let's begin. We begin with a blank number line. And yes, I am aware that is not the way you spell begin. Moving on. This number line consists all the real number lines, which it contains all the real number lines. And our goal is to find all the numbers that exist on this number line. And so you see this scripted R right here. This is the symbol that represents all the numbers that exist on the number line. And so the first thing we're going to begin in our exploration is a concept called natural numbers, which you see right here. We use a scripted N to stand for all the natural numbers. And the natural numbers count objects you can see, touch, and feel. And that's what we put in these blanks. Note that the number 0 does not meet the above criteria. So think about that. Why does it not meet the above criteria? Well, you can't see nothing, you can't touch nothing, and you cannot feel nothing. Therefore, 0 is not a natural number. Now, to start off our topic, natural numbers, they are the first numbers that we learn about as small children. And indeed, these would have been the first numbers that we would have been aware of back at the beginning of time. So imagine, if you will, a child or someone else who is tending sheep or some other animal, and they've got a sheep. Don't judge my drawing of my sheep, please. Their sheep goes out to the pasture all day, and the sheep goes back in at the end of the day. Now let's say our shepherd, he or she wants to make sure, of course, that all of the sheep are back in their pen at the end of the day. So how do they do this? How do they count all the sheep that are missing? Or to see if any sheep are missing, I should say. Well, let's say it's a rocky area, there's stones, and one sheep goes out, they put one stone down. Another sheep goes out, and put another stone down, and so on and so forth. Let's make these circles instead, right? Putting little stones down. Now, he's got his pile of stones. A sheep comes back in. He takes the stone out. Little indentions left. Another sheep comes out, back in, I should say, right? And so on and so forth. And he does this until all the sheep he sees are back in. He sees one stone is still hanging out right there. So what is he to conclude? He is to conclude that he needs to go out and find that missing sheep. And what he's done is he's just concocted a number system, a system that consists of things you can see, touch, and feel. So we've got our first numbers here on our number line, starting at 1 to 2 to 3, 4, and it goes on as high as we can count, on to infinity. And note, even though it's not a part of the number system, when he takes the stone out from the sand, leaves a little indentation, like a circle or a 0. I bet there's some significance to that. Next, we move on to integers. Now, note that all natural numbers are integers, right? Integers also count objects you can see, touch, and feel, and they include 0 and all negative whole numbers. So filling in our number line here, note we've already got the natural numbers here because we already knew about those. But with the addition of the integers into our number system, we get 0, -1, -2, -3, and -4. Now, it might seem obvious that 0 is a number because it fits so perfectly in our number line, but it is worth noting that you go back into ancient times, 0 was actually considered a very controversial subject, going at least through the Bronze Age. Note that our years, they start at 1 AD, not 0 AD. So we move on to rational numbers. Rational numbers is the first entry into numbers that exist in between 0 and 1, or in between any of these integers. And so rational numbers are derived from the earlier defined set of integers, which again we use the symbol z to represent all integers. They're also called whole numbers. And a rational number is the ratio of any two integers. And this is, of course, provided that the number on the bottom, the number you're dividing by, does not equal 0. So we write our definition like this. All right, little squirrely bracket there, and p divided by q. P and q are just numbers. And we draw a line here. This line means such that. A lot of the times people write an ST instead of such that. It means the same thing. Which one you write down, that is your preference. So we say P divided by Q such that P and Q belong to the set of integers. And Q does not equal 0, as I was talking about before. We cannot divide by 0. That would become something that is undefined. So again, we have brackets like this. We are defining a set. And our set is all numbers that can be written as P over Q such that P and Q belong to the set. That's what this epsilon here symbol means. Belong to the set of integers. And also Q does not equal 0, right? In other words, it's the ratio of any two integers such that you're not dividing by 0. So again, note that just like integers included the set of natural numbers, so do rational numbers contain all of the integers and natural numbers for that matter. For example, look at 2. 2 can be rewritten as 2 divided by 1. That is a ratio of two integers. Or 4 divided by 2, right? There's any number of ways I can represent the number of 2 using the rational number convention. All right, so the rational numbers, these were developed by Pythagoras, and he had this rational worldview that all numbers could be represented in this fashion, right? One whole number divided by another, like a half, a fourth, an eighth, a 16th. Like these are all rational numbers, and you could represent all the numbers in between the previous integers, like for instance between 0 and 1, 1 and 2. So we're going to explore this idea by exploring as many rational numbers as we feasibly can in the time we have using this convention. So we've got q divided by p, and we're just going to do this little scheme here where if we go over 1, we stop. If we repeat a number, we don't count it because we only need to count each number twice. So here we have it. So q over p, so we'd say 1 divided by 1, right? That's our stopping criteria. So we go to the next one. 1 divided by 2, which is a half. So far, so good. And then we have 1. So that's our stopping criteria. All right, so we're going to be graphing these on this number line down here as we go through them. And so we have 0 on one end, and we've got 1 on the other end, and we just found 1/2. And so 1/2 right there, right in the middle. So let's move on. Now we do 1 divided by 3. 2 divided by 3, and then 1. And 1/3 goes about right here. And 2/3 goes right there. Moving on, we go here, 1 over 4, right, 0.25, a quarter. And so 1/4 is right here. And we go here, 2/4, which is the same as a half, right? That's a repeat. We don't need it. So we go to 3/4, 0.75, 3/4, and 3/4 exists right here. Okay. And 2/3 is right here. This dot here is just a smudge from the other side. Next, we go to 1/5. 1/5, that's 0.2. 1/5, that exists right here. And then we go to the next one, 2/5. 2/5, that's less than a half, and that goes right here. Right? That's 0.4. Next, we go to 3 over 5. 3/5, that is 0.6. 3/5 exists right here in this spot right here. And then we go to, that's a 5 there, okay. 4/5, that exists right here. And then we hit 1, and that is our stopping criteria. And you can see we could keep doing this, right? I could draw a 6 here, and then we would have 1/6, 2/6, which is a third, so that'd be a repeat. 3/6 is a half, right? Another repeat. But then we would have 5 over 6. That would be a new one that we would add, and 5/6 would exist somewhere over here, and you'd keep going. And eventually, you can tell that if I were to keep including numbers down here, keep bringing numbers out as needed, I would fill all the space right here with just so many lines. It'd be right on top of each other, right? It would be a dense area. And so the ancient Pythagoreans had a rational worldview, as it says right here, that all numbers could be described as rational. But it should be noted this is not the case. Even though we can fill all these voids with an infinite numbers, and it seems like that should be sufficient to fill that space. It is in fact not. And it can be mathematically proven that some numbers are not rational numbers. And this brings us to the set of irrational numbers, as in not rational. So irrational numbers, and we use this Q tick. A lot of the times I'll see a Q with a C. C generally stands for complement, but a tick mark is just fine for this class. And so an irrational number is any real number, right? Any real number that is not a rational number. So it should be noted, the other sets that we've seen so far have been defined by what they are. This is the first number we've seen that is defined by what it is not. It is defined as a real number, but its defining characteristic is that it is not a rational number. Traits of an irrational number. The decimal expression of an irrational number has an infinite number of decimal digits in a non-repeat way. So these two things are important, right? Because a third is 0.333333, right? And it repeats forever, right? Even though it has infinite number of decimal digits, they are repeating, right? And it can, anytime that the decimal pattern repeats, you can represent that as a ratio of two numbers. But if it is non-repeating, then you cannot represent it as the ratio of two whole numbers, two integers. Now you've seen the question posed right here while I've been talking. Pause the video for a second if you've not already thought of any irrational numbers. See if you can think of some, and then hit the unpause button to find that one of the most famous irrational number is pi. And pi is defined as the ratio of the circumference to the diameter. But that's what it is. Does not matter the size of the circle. It is always the ratio of the circumference to the diameter every single time. Doesn't matter if the circle is the size of an inch or if the circle is the size of Corpus Christi, right? It is always going to be defined as the circumference divided by the diameter. Now, another famous number you may or may not be aware of is the number E. E was developed for finances. But it turns out it shows up everywhere in nature, and so E is defined as the limit as m approaches infinity of the expression 1 plus 1 over m raised to the n. Note how when you take this limit, this number will be vanishingly small, but you're taking an infinitely large exponent. And so it essentially ends up being 2.7 and a lot of decimal places, so many that they are infinite. And of course, pi, that is roughly 3.14. How many decimal places do you need depends on the application you are doing and how much precision you require. So some other irrational numbers are square root of any prime number, such as 2 or 3 or 5. Or any composite number involving a prime. Or should I say a lot of composites involving prime. There are some exceptions to that, of course. Right, 6 times 6 would be 2 prime numbers, but the square root of 6 times 6, of course, would just be 6. Right, square root of 10, etc. But the square root of any prime number will be irrational. Okay, so I want you to note that the square root of 4, even though it's inside a square root, is a rational number, not irrational, because this equals 2. So therefore, the square root of 4 is a rational number. All right, so note that irrational numbers are defined by, oh, we already said that. So as a reminder that they're not. So we will take a look at this. So we've got our set of real numbers. And we have our set of rational numbers hanging out here. And we have our set of irrational numbers right here. Okay. Note that I intentionally made this portion larger. Right, the portion of real numbers that are irrational larger than the set of rational numbers. That's because it actually can be shown again that they're infinitely more irrational numbers than there are rational numbers. But regardless, the set of real numbers will be simply the union of the set of rational numbers with the set of irrational numbers. And so this further says that the set of irrational numbers is defined as the set of real numbers such that our number, whatever happens to be, does not belong to the set of rational. Right? This is our formal way of writing it out. And technically, I should define x right here. X belongs to the set of real numbers such that x is not an irrational number. That's it. That's our definition. And I know that this might look like a tick mark right there. That's just a little bit of the font on the R. That's just a regular R. There is no tick mark right there. Moving on. So it may seem that we've filled up the entire number line. But what about the square root of -1? Where would that exist on our number line? What is the square root of -1? Come back here for a second. Along here. Well, the answer to that question is that it doesn't. It does not belong anywhere on this number line. In fact, we have to come up with a new designation and come up with something called the complex plane. So a complex number, let's go ahead and define that while we're here, is any number that can be expressed in the following manner. And we use a scripted C right here, a fancy C, if you will. And so it is A plus BI such that A and B belong to the set of real numbers. Right, so for instance, 1 plus 2i, 3 plus 4i, and note that all real numbers are also complex numbers because part of the definition, A and B have to belong to the set of real numbers. Well, what belongs to the set of real numbers but 0? So if there is no, so the number 0, which belongs to the set of real numbers, if that's what B equals, right? 2, we'll say 2 equals 2 plus 0i. Well, A and B, A is 2, B is 0, fits this definition. Therefore, 2, while also a real number, is also a complex number. And complex in this context just means that it has multiple parts. And so note that this number has 2 parts, right? It's complex. It doesn't have just one part. So let's go ahead and look at x squared equals -4. Oh, and I should note that I is defined as the square root of -1. That's very important that you know that. So square root of -1, right, which does not exist anywhere on the number line, but that's why we appeal to the complex plane. And so this complex plane, which has a real axis, which we use RE, and an imaginary axis, which we designate with IM. And we look at x squared equals -4. We want to graph this. So x equals the square root of -4. And so we would write -4 as, oh, I should say positive or negative. Positive or -2 times the square root of -1, which we define as I. So positive or -2i. So note that the real part is 0. And the imaginary part is positive or -2. So we would graph this here and here. Right, this is positive 2i. This is negative 2i. Okay? And if I wanted to graph another number, let's just say, oh, here we are down here. z1 equals 2 plus 3i. So we notice the real part is 2. So we come over here, 1, 2. The imaginary part is 3i. So we go up 3. And so our number z1 is right here. Okay? Now we look at the next one, z2. z2 is -1 plus I. So the real part is -1. Real part is, imaginary part is +1. We put that there, and that is our z2. Okay, pretty straightforward. Next, we have z3, which is -2 minus 3i. So real part is -2. Imaginary part is -3. So we put that right here. That is our z2. 3, z3. Sorry about that. z4. z4, that's 3 minus 2i. So we come over here. Real part is 3. Imaginary part is -2i. So we come down here. And we put our z4 right there. Last but not least, we have 2. z5 is 2. Right? Again, note that's the same as just the number 2. The real part is 2. Imaginary part is 0. So there we go. That is z5. All right, there we have it. That's how you graph a complex number on the complex plane. And note how this bears a big resemblance to the XY coordinate system as well, which we will be getting into later on. So again, this is called the complex plane. Which is not the same as an X and Y axis, though it does bear a similarity. And we want to note that all real numbers are also complex numbers, as I just said before. So all real numbers are also complex numbers. Because the imaginary component of any real number is, like I said before, 0. Okay. All right, so now we're going to draw a Venn diagram of all the number sets so we can see how they all go together. So all numbers, at least all numbers that we know of, are complex numbers. And inside the set of complex numbers, we have the set of real numbers. Okay, and remember, complex numbers, that's a plus bi, 2i, 3 plus 4i, so on, like any number that looks like this. And the real number is whenever b equals 0, this b is 0, you're inside the set of real numbers. And so inside the set of real numbers, you have the set of rational numbers and the set of irrational numbers. Okay? And then inside the set of irrational numbers, right, you got square root of 2, you got pi, you got e, etc. And for the rational numbers, inside of here, we've got all the integers. And the set of integers contains all the whole numbers, both positive and negative, and includes 0. Inside the set of integers, we have the set of natural numbers. Right? And that's it. And you can subdivide this set between positive and negative whole numbers, if you will, but we're just going to keep it simple and just list natural numbers and say all whole numbers, including negative, positive, and 0, are integers, and leave it at that. Okay, and so there it is. So now I want you to put the video on pause for a second and think about this question. Describe a rational number with words. Okay, and now that you've had a chance to think about it, let's go ahead and just write one down as a class. A rational number is a ratio of two integers such that you do not divide by 0. So again, a rational number is a ratio of two integers such that, remember we're using a line to symbolically represent the word such that, you do not divide by 0. And that's it. That is, in words, what a rational number is. So finishing off the bottom of the last handout here, we have these numbers. We're going to list the sets that they belong to and go ahead and plot them on the number line. So for 7, we immediately see we need to extend this out a little bit. There we go. So 7 is a natural number, right? You can see 7 sheep, right? It's also an integer, right? Because it, by virtue of simply being a positive or negative whole number. And then it's also a rational number. Why is it a rational number? Because I can express 7 as 7 divided by 1. It's also a real number, and it is also a complex number. Right? It belongs to all of those number sets. Now let's look at 0, and we'll go plot it there first. Okay, let's look at 0. 0 is not a natural number because I cannot see 0 objects. But it is an integer, right? It is a rational number because I can express 0 as a ratio of 2 integers, right? 0 divided by 3 is 0, right? I can divide any number into 0. I just can't divide any number by 0. Okay, 0 is rational. I'm sorry, it is rational, but it's real as well. And it is also a complex number. And so plot that right there. 2/3. It's not a whole number, so it is neither natural nor an integer. But it is a rational number, 2/3. And all rational numbers are real numbers, and all real numbers are complex. Now let's look at D. Note that D is a ratio of 2 numbers, but this does not make it rational because square root of 2 is not a rational number. So we would say D is irrational. And all irrational numbers are real, and all real numbers are complex. Okay. Forgot to graph 2/3, so that'd be about right there. And then square root of 2 divided by 2, that's going to be less than 1. That'll also be a little bit to the right of that. There we go. -8/3. This is a rational number, which is also real, which is also complex. And -8/3 is equivalent to -2. And -2/3, so let's extend this line a little bit. And we'd graph that about right there. 2.5 is rational. Right, it's not a whole number, so it's obviously not natural or an integer. But why can I say 2.5 is a rational number? Well, note that the decimal place does not go on forever, so that's kind of my telltale sign. But I can express 2.5 as 5 divided by 2. Right? And that would put us about right there in the number line. All right. And so 2.5 is a rational number, which is real, which is complex. And that's what we have for today's lesson. So we went over all the different sets of numbers. We went over how the real numbers are broken between two different sets, rational and irrational. All real numbers are either rational or irrational. No one number can be both rational and irrational. And inside the rational, we've got the natural numbers, and contained by the natural numbers are the set of integers. And note that covering everything is the set of complex numbers. And we looked at how to graph regular numbers on a number line, but when we got to numbers that were outside the set of real numbers, we had to appeal not to just the number line, but to the complex plane, like we did here. Okay. So that is it for today's lesson. Have a wonderful day.